Okay. Okay, sorry for the wait. So this is second part of today's session. So Alex Bivolcic from State University of New York at Buffalo. Alex is a PhD student of Bivolcic and nice collaborators, and he will tell us about integral reduction of KP-Whitham modulation system.
So thank you, Tonio, for the very kind introduction, and thank you to everyone at the INI for giving me the opportunity to speak to you today. This is some work that I've been doing, as Tonio said, with my advisor, Gino Biodini, and then collaborators, Mark Hooker and Tony Morrow, on integrable reductions of the KP-Whitham modulation system. So a general roadmap of what's to come. I'm going to do a brief background on nonlinear waves in two spatial dimensions. I'm going to introduce the KP-Whitham system and briefly go over its derivation. And then we'll get into my current work, which ultimately would like to answer the questions of integrability of the full KP-Whitham system, and then looking at various reductions of the system and future goals from there. So first up here, we have the KBB equation up at the top. This is I'll try to be pretty good for the people watching online. But this is a 1 + 1 dimensional prototypical nonlinear wave equation. It's a universal model. Its Whitham system was the first Whitham system back in '65, so it's been around for quite a while. Plenty of people have done work on it. The KP equation below is a 2D analog, so you can see it contains KP within it, and also a universal model. It has two types, right? So we have this sigma can be plus or minus 1. In the event that sigma is -1, we have strong surface tension, and then for +1, weak surface tension. My work is going to be for general sigma, so sigma will just be a parameter throughout. Now, there was an abstract formulation of the KP-Whitham system back in '88, but the system that I'm going to be using was derived in 2017 by Bivolcic, Biodini, and Wang. So real quick, bringing up, highlighting some applications. The KP equation is a universal model, so it appears in plenty of places. Water waves, rarefied plasma, Bose-Einstein condensate, optics. And I would be at a loss if I didn't include a pretty picture of a nice 2D wave pattern, just to make the presentation look rather nice. But yeah, so let's get into the KP-Whitham system now. So I've rewritten the KP equation in evolutionary form. This is going to be more useful for the derivation of the system. This is what they end up using. And we're going to be doing this with small dispersion. So epsilon squared, the coefficient on the dispersive term, is going to be very small. It'll be a weak dispersion. Now, it's worth saying that there hasn't been a lot of work on multidimensional Whitham theory in general. The derivation follows the same general procedure as 1 + 1 dimensions, but there will be some added complications along the way. So if you do work in modulations, this will probably look familiar. So we're going to do a multiple scales expansion, and then from there we'll define our local wave numbers through that rapidly varying phase. So K to the X direction, L, and then omega is our frequency. Now, when we impose equality of the mixed second derivatives, we get 3 compatibility conditions. Normally in 1 + 1 dimensions, you only get 1. And ideally, we would have only gotten 2, but the fact that we get 3 is going to come back to bite us later on. So it's an important note worth taking. And then when you go further through the process, you get 3 additional modulation equations by removing secularities at next to leading order. So the sticking point here is I can express the entire system in just 5 parameters. So what I have now is an overdetermined system if I include the 3 compatibility conditions and the 3 additional modulation equations. So historically, the way you kind of get around this is you include the first 2 compatibility conditions because they're in evolutionary form. You include those in what I'm going to be calling the closed 5 by 5 system, and then you treat this third condition as an initial constraint at t equals 0, because it's completely maintained under time evolution. And that's kind of how you get around this. But again, an important point that we're going to have to come back to later. So at that point in the derivation, you would have the Whitham system in physical variables, just like KDV. The system in physical variables is very complicated, so it's not up on the screen. What we do instead is we introduce what we're calling Riemann type variables. These are actually the Riemann invariants of KDV. Since KP is a 2D analog of KDV, this simplifies the system immensely. Right? It really helps out. And we can get our periodic traveling wave solution in terms of these, as well as the elliptic parameter. Right? And then there's two generally distinguished limits. You have the harmonic limit when your elliptic parameter goes to 0, the solid sum limit when m goes to 1, and there was subsequent work that was done with these two limits in the KP-Whitham system. So just in summary of where we are for the derivation, we have a 5-component quasi-linear first-order system of PDEs and an initial time constraint. Our parameters are the 3 KDV Riemann invariants, this directional parameter Q, which controls the local inclination angle, and then an integration constant that came along the way, P, that we couldn't drop. So you could put the system in a very simplified vector form, then it looks pretty. But if I show you the full system in component form, it gets rather large, but no need to worry, right? So there's a lot of coefficients here, but it's nothing too scary. The uppercase V's are the characteristic velocities from KDV. The n's are from cylindrical KDV. And it's worth noting, so the first 4 equations are in evolutionary form. And then the 5th one is, kind of like a constraint, as well as, our curl-free compatibility condition from earlier. It's also worth noting the KP-Whitham system preserves all the physical symmetries of KP, and the KP-Whitham system does simplify down to the KDV-Whitham system, right? As long as you take Q to 0 and you drop derivatives with respect to Y, right? And then that simplifies immensely. So the open questions here, is the KP-Whitham system integrable? And if so, can I find some Riemann invariants of it, right? Diagonalize the system and pat myself on the back, right? Well, oftentimes when I bring this up, the question I get from other people I ask, what do you mean by integrable? What are you using in this case? Well, for us, the bar we're trying to cross is this Haantjes tensor test. So given a square coefficient matrix, I can construct a tensor which at least in 1 + 1 dimensions, when that's vanishing, that is necessary and sufficient to show integrability. Now, in 2 + 1 dimensions, this is only necessary. It's not sufficient, but I'd love to at least cross that bar of necessary, right? Then we can go from there. So our goal is to get this vanishing tensor. So initially, the full KP, or the 5-component closed KP-Whitham system, does not pass that test. Which was kind of surprising. We know that KP is integrable through the IST, so we would have expected it to pass. So our next goal was to look at various reductions and gain some intuition that way. Right. So I have 3 systems: one that's independent of X, one that's independent of Y, one that's independent of T. And it is worth noting. So even though the Whitham system, right, does not depend on one of these independent variables, we still describe full 2D wave pattern, right? Because that inclination angle can vary, and then that gives you a full 2D wave pattern. So let's jump into the first system. First system was the YT. This one ended up being the easiest to work with, so it's good that we started with it. Initially, I get a 5-component system. I just drop the Y derivative terms. Just trying the test on this immediately, it fails the tensor test. We can reduce this, simplify it, make it a little bit easier to work with through a quick change of variables. If I introduce these new S variables, what happens is we just remove P entirely, that integration constant from the system. And additionally, it's worth noting that elliptic parameter, which used to depend on all three Riemann invariants, now only depends on S3 and S2. And that's worth noting because now what I can do, I have this transform system 16. The PD for S1 is essentially decoupled, right? So none of the coefficients depend on S1. S1 doesn't appear in any of the other equations, so we can kind of drop it. It's decoupled from now, and look now at the three remaining equations. And then we tried testing this again, still failed the Haantjes tensor test. So still an issue. Nevertheless, we bravely just push forward. We look for Riemann invariants anyways. In this case, when we go through, there is a simple eigenvalue, 2 sigma q, simple both, no multiplicity, but it's short. And it has the characteristic relationship given by equation 21. It gives us a relatively simple Riemann invariant, right? So I have one of them at least. And with one of them, I could at least partially diagonalize and go from there. But hold your horses real quick. Let's jump back. Okay, so if I take into account the entirety of all three compatibility conditions, I see that in this reduction, the wave vector k, or the wave number k, is a constant of motion, right? Why is this important? Well, if you look carefully at R2 and then the definition of k, which just comes about during the derivation of the system, they're proportional to each other. So my Riemann invariant is a constant of motion of the system. So what do? Well, I partially diagonalize through a transformation, and then the PDE for R2 is trivially satisfied. So we can just leave that aside, and we're left with a two-component system, and two-component systems are always integrable. So there we go. We did it by taking into account, the full compatibility conditions. We were able to give this to a integrable system, and then we have an integral form of the remaining two Riemann invariants. Have been able to integrate that, but there we go. And so a quick summary, because the other two reductions are going to follow the same procedure. We're going to start with the closed 5-component system, right? We consider solutions independent of X. We attempt to just further reduce or simplify the system down from there. We find a Riemann invariant. We hope, or we expect at least, that once we enforce the full compatibility conditions, that Riemann invariant will be a constant of motion. And then we can partially diagonalize the system and test for integrability. So we're going to do this twice more. But since we've done it once, it'll be easier. Right, so now we look at the XT system. So these are independent of Y. Simplifying this system is actually much easier. So you can just directly substitute in the definition of dPdx and remove P as a parameter from the system. So we go down to 4 components with not much work at all. As expected, neither of these systems are integrable. So or at least they fail that test. So in this case, when you look at the system, we expect the wave number L to be our constant of motion. So we look in the system, we do find L is a Riemann invariant of the system, as expected. So once again, we partially diagonalize. We can neglect the PDE as it's trivially satisfied. We get a 3-component system, and it passes the Haantjes tensor test. So we now have an integrable 3-component system. Now, something that's pretty nice about this, you may notice, so 3 components, and my parameters are the KdV Riemann invariants, right? That's got to be handy, right? And in fact, what you can do is you can express that coefficient matrix as a deformed KdV system. So I take the diagonal, KdV, and then I have a deformation of order L squared. So with this, you can do a perturbative series. You can get the perturbed eigenvalues and perturbed Riemann invariants. Getting the true eigenvalues and Riemann invariants of the system look pretty ugly as far as coefficient matrix goes. This is as far as we have been able to get. But here we are, 2 systems down, right? 1 to go. The XY system, so these are stationary solutions. Now, ideally, we want to follow the same process, right? So we're going to try to reduce this down. Unfortunately, thus far, I haven't found a way to reduce the number of parameters in the system. And then we're looking for omega to be Riemann invariant, but omega isn't a Riemann invariant of this 5-component reduction, right? And it fails the Haantjes tensor test. So it looks like you're at a brick wall now. And what ended up happening, historically here is we just kind of force it, right? So we go back, thus far in the 2 previous reductions, we learned you have to consider the full overdetermined 6-component system. You have to take it all seriously. I can't just look at that closed 5-component system and get a full story. So I just changed the equations that we chose to keep in the closed 5-component, right? So now I'm using 34A and C in the 5-component closed system, and then we're making 34B kind of like a constraint. But then again, none of these equations are evolutionary, so the term constraint has less meaning here. But now I've slightly changed to a different 5-component closed system with an additional constraint, and now we're going to try it again, right? So still not reducible. However, we can kind of put this in evolutionary form, and the frequency omega is Riemann invariant of this different system, right? So we have our Riemann invariant. Once again, when you take into account the full compatibility conditions, omega is a constant of motion, so we can partially diagonalize, neglect that PDE is trivially satisfied. You get a 4-component system out of that. And we test that system, it passes the Haantjes tensor test. So now we have 3 integrable reductions of the KP-Whitham system. So, what can we conclude from all of this? Well, first off, it's definitely necessary to consider the full overdetermined KP-Whitham system, right? So, as I've said a few times, historically, that wasn't necessarily the case, right? So we just grabbed 5 components. And because you need a square matrix to at least feed into that test, and square matrices a bit more sense to us, but it seems that that's not the case. In each reduction, we do have a Riemann invariant which corresponds to a constant of motion once you take into account that full overdetermined system. And then finally, once you neglect that Riemann invariant because it is a constant of motion, the resulting system passes the Haantjes tensor test and therefore should be integrable. So what do we hope to do from here? Well, twofold. So first off, we'd like to use this intuition to figure out the correct compatibility conditions to make the full system integrable. Right? So as I mentioned before, this tensor test is only going to be necessary. It's not sufficient to show that the system's integrable, but I'd like to at least cross that bar if necessary. So that's one direction that we'd like to go into from there. But then also, we have 3 perfectly good reductions. So we can do some more work with those and application, right? So previous applications with solitons are on the board there. We'd love to essentially look in that direction, but with these reductions instead and not necessarily in a soliton. So a bit early. Still faster than I expected, but otherwise that's what I have for you today. So thank you for your time. Any questions?
Sorry, but so when it passes the Haantjes tensor test, so it is necessary and sufficient if it is in 1 + 1.
Yes.
And so the previous one that you showed, which one was actually? So that one is 1 + 1, therefore it's in.
Yes. So
okay, but these reductions that you, if I understand, making these reduction level of these Whitham, what do they correspond before Whitham? I mean, at the level of the full layer.
At the level, so what do the various reductions correspond to? So
are these the Whitham equation of some reduced integrable system, or they are just reduction of the Whitham equation?
It's a good question. So we're still making a full 2D wave pattern, right? So it's more of the way that I've thought of it thus far. It's our modulations, right, are independent of one of these independent variables, even though we're still, we're still working with a full 2 plus 1 dimensional KP with or KP solution, right, at the end of the day. That's all this because I've thought into it personally.
Yeah. So really, expression here, KP has the entire gravity formation.
Sure.
If you use those, you help the just like you use for the class.
Sure.
But you do have a meaning.
Yeah, you can do so many conservation rules is what you were saying. Yeah. So well, conservation rules is even part of that. I'm not necessarily I haven't considered that direction yet either. Going in with more conservation rules. But it's a good direction to look into.
I think because you start from the middle system.
Yep.
That's also and then you use some particular thing. Then you have the 500.
Sure.
But you did the correctly and it's
I'm not sure.
now also this things like this. It's really dependent on the program.
The tensor doesn't depend on the coordinates. I don't.
No.
Yeah, I don't think so.
It's expressed in specific coordinates.
Yeah, but it's vanishing.
Yeah.
But the key is that the system is overdetermined. So you have a constraint on the initial conditions. So and possibly this requires functional dependence between these coordinates. So it's not to single out the sub 5 by 5 system. It's not integrable in the sense of the Haantjes tests. But the underlying system is overdetermined. And this means that it's not automatically integrable. So probably there is a functional constraints between these, but they are not necessarily all independent. If you look at the conservation laws, they won't be automatically compatible. There must be some constraint.
It's maybe a stupid question. Why is there no difference between KP1 and KP2 in this?
In this, well, just as far as like from a more pragmatic perspective, right? It's just going to change the sign, the future for me. So the various analyses that I'm doing, I guess the point of view we're coming from, we expect both of these systems to be integral. So we're trying it for arbitrary sigma. But it really just doesn't get in the way for testing integrability of any of these systems. I can do it for arbitrary, sigma plus or minus 1, and it doesn't impede my calculations.
It may make a difference. I want to do some kind of other analysis. Right?
Yeah. Yes.
Believe that this system of generalization. You actually also consider the setting the interest tensor to 0. Consider that 0. Hidden relation between variables that allows you to.
Sure.
You really could use that angle to actually get your relation between variables.
So pragmatically, again, the I'm not sure how useful it'll be for it. The tensor is very big and very scary looking. I'm not entirely sure if we would be able to exploit it. But the different perspective is nice. If intelligible, it may give us some insight, but very big, especially, with, when I calculate that tensor on, a 3x3 system or something, right? It's possible. With this 5x5 system, just putting the matrix in evolutionary form, like it is in 37, that matrix is already too big to even fit on page, let alone the tensor that I'm calculating from it. So it would be a lot to decipher through.
Another element of part of this. So I don't think that in principle you can use the undiscriminated condition as a tool to classify it, because if you assume if there is a constraint, you need to embed this constraint at the beginning, and then you derive a different system in that case, then you apply the undiscriminated test, this different system. Set of coefficients will be different. So if you assume that all the fields are functionally independent, you get one system. If you introduce a functional independence, you will get a different system. And then you calculate the undiscriminated on a different matrix. So I don't think you can use it. Because you calculate the undiscriminated rather than assumption that all the fields are functionally independent, and you get the response of this. If you introduce the assumption you in a different system, you calculate the undiscriminated of a different matrix, and then you cannot use your idea. The idea you suggest, so use that condition to classify. Although I'm still saying it's quite, I'm not sure if it's effective. How effective it is.
We do some in a sense, we have this go up on the
Yes.
what you said.
Yeah.
See.
Actually, also, no, that's in this case it's particularly complicated, I'm saying. But all the classifications that has been done so far have been done exactly that way. So by looking at the anti-tensor and then incorporating the further the component of the problem. Seminar sessions will be seen next week on Tuesday at 11. So, and we have 3 talks as now usual. So Tuesday, Wednesday, and Thursday. Next week, speaker will be Dmitry Kadomtsev on Tuesday, Marco Bertola on Wednesday, and Katie Oliveras on Thursday. Okay, so more details will be simply by reception.